Hello everyone. So let us start. So today we are continuing with the contents of the last lecture that we were discussing on gradient descent algorithm. And in that continuation then we'll be talking about the feed-forward neural networks, and we will be focusing on multi-layer perceptron model and radial basis function neural network model. Okay. So in the last class, we had seen that the error function is defined as summation ti square, and then we replace the contents for ti as yi. I is just the index to represent the ith sample, and then there is the function g, which is known as the activation function, and then there is a complete hypothesis HWXI, which is basically the weighted sum of the input. So with this, I'm not going to into the much detail of this. It is just a kind of a recall of what we did in the last class. Then I'll be focusing on how the obtained weights are used for training, and then further how they can be used for testing. Earlier classifiers were focusing on finding the decision boundary parameters using the neural network. Now we have the error function as EW, and based on this we are trying to optimize the weight parameters, right? So the functions and then appropriate weight parameters. These weight parameters are going to be used for testing purpose. So we had seen that h is the function of w, g is the function of h, ti is the function of g, and e is the function of ti. Making use of that, for the partial derivatives, we had this chain rule. Then we had talked about individual differentiation, and say for example this ti expression was differentiated with respect to the function g, and we had got -1. Similarly, assuming that the function g is differentiable, we had obtained g dash as the first partial derivative of g with respect to h. And here hwxi, which was actually equal to w1 x1 plus w2 x2 plus wn xn, is giving us its partial derivative of del of h with respect to del of wk as its coefficient of wk, which is equal to x of k. And everywhere you see this index I in blue color, this is representative of the sample number, right? So is this part clear? Yeah, anyone? Are you able to hear me? Yeah. So is this part clear? Fine. So can you explain why del h by w del wk is xk? That means if it is a partial derivative over the sum of these w1 x1 plus w2 x2 plus wn xn, then it is equal to the sum of the partial derivatives of each individual term, right? So we can write del of h by del wk as del of w1 x1 by del of wk, right? Because there is w1 involved in this very first term, and then we are applying the partial derivative in the direction of wk. W1 and wk being orthogonal, their derivative gives us a 0. So anything other than the kth term in this expression of weighted sum, we will get 0 except other than the term which is xkwk. And xk being the coefficient of xkwk, right? So del of wk by del of wk becomes 1. Is this part clear? Are you able to recall your school mathematics? Fine. So then del of E by del of Wk is identified to be equal to minus 2 summation over all the samples I, Ti multiplied by G dash Xk, and this Xk refers to the kth feature of ith sample. Right? So this is how you have obtained del E by del Wk. And when you will put the expression for Ti in equation 5, you get del E by del Wk as equal to minus 2 multiplied by summation over all i's, the expression y minus GHX multiplied by G dash multiplied by Xk, where this expression is for each individual sample I. Right? So then the weight update in the direction of Wk is given by delta Wk, which is equal to minus 2 summation the same term multiplied by G dash multiplied by Xk. And when you are dropping out 2, then you get this expression. Fine. So basically what you have obtained is the change in the value of Wk, right? This change is identified as delta Wk. So if we are walking in on the earth on the error surface, we need to change my step in a particular direction. The direction will be given by these k or n dimensions in that space, W1, W2, W3 and so on. So in each direction we measure this infinitesimal change, and then we come to know the new feature, a new vector of weight, new weight vector to explore with. You understand that this is a kind of guiding heuristic which is taken greedily to change the old value of W. The change in the old value of W is obtained by this delta Wk, right? So for each dimension k, we will be obtaining such changes, and then the new weight coordinates will be obtained. Say for example, if we take two-dimensional weight space, which is defined by W1, W2, then my new weight to explore with will be given by the weight vector W1, W2, where W1 is obtained by subtracting delta W1 from the old value of W1 and delta W2 from the old value of W2. Of course, I have not marked these W1 and W2 with their indices of old and new, but being a person in computer science, you know what is written at the right hand side of the assignment operator, which is represented by equal sign here, has an old value to refer to, and what it computes as an expression on the right hand side will then be written in the memory location of the same variable name. Right, so this is how we represent the new value. So what is on the left is the new value, and what is on the right is the old value of W. Fine, and then it is actually computed with the change by minus delta W1 and W2 respectively. So what is happening is, suppose you were trying from this side, say for example, I'll change the color of the pen. Suppose you were trying with a point randomly chosen as this blue point, then you started with some point W1, W2 on this W1, W2 space. Are you able to recognize the space? This W1, W2 is a two-dimensional space on the floor. It is like the floor. And the third dimension is the dimension of the error. So when you started with this blue point on the surface, basically you started with this point on the ground, on the floor, which was actually the old W1 and old W2, right? So we started with this, but where should we move to? What should be my new W1 and W2? Suppose I wanted to come to this direction, whether this will be the best direction to come to, or whether there should be another direction to go to, so that in the best possible time we find the global minima. So we had taken a greedy strategy to come down to the direction which has the steepest descent, the steepest slope downwards. With that, we had obtained this delta W1, okay, and similarly delta W2 using the same expression which we just obtained. So if I have to move in this direction, I'll show you with a different color here. I'll show you how much I'm going to move to the new direction. So somehow the animation is lost. I will show you again. So I'm taking this point as W1, W2 on the W1, W2 plane. Let me say that this point moves to another point, right? Okay, so the one which I have drawn first, right below this blue point, is my old point. So let me write this. So this is old W1 and old W2. This point is a point here. Just 1 minute. So let me say that this point is the old point, okay? And I want to move to the new point, which is here, right? Are you able to see this difference? The old point is right below the blue point on the weight space. Weight space is two-dimensional here in this example, while the third dimension is the error dimension. So now if I have to move to the direction of new, you will see that it is taking a component in this direction. So actually there is a problem with this pen, that it doesn't pick up something which is already there. So somewhere it is actually moving in both the directions, right? Please just give me some time. Suppose I wanted to move it to somewhere here, okay, and then I will have actually moved my W1 from this old position to something lesser, right? So this could have been my new W1, okay. So this could have been my new W1, and what I'm showing you on this side is my new W2. So the new coordinates will be new W1 and new W2. Fine. So what I mean to say here is that when you are moving downwards, it is not just along one axis of W1 or not just along with the other axis of W2. It is a kind of diagonal movement sometimes. It may be. Right. So if it is a diagonal movement, that means you would have taken some step towards the direction of W1 and some step size towards the direction of W2. So that is how the new W1, W2 will have something as W1 minus delta W1 and W2 minus delta W2. Fine. Is this part clear? So now if you have moved to this area, this new point, that means you are actually putting your search somewhere here. Yeah. So basically corresponding to this new point, you are looking for the point somewhere here. And this error is definitely reduced by moving into a new direction. Fine. Similarly, if you keep moving in the steepest descent direction, you are likely to get to the global minima in 1 or 2 steps, or maybe in 10 steps or 20 steps, but it is somehow doable. There is a slight problem when your step sizes were very small. Then you would have come to this point, you would have come to the next point, and you would have got trapped in the local optima. So that means the step size matters as well as the initial random position of the weights would matter. Had you started with the other direction where there were no pits in between, whatever could have been the step size, you would have actually come to the global minima for sure. Are you getting the point? So I'm having 2 points to mention. One is about the step size and another is about the initial random start. Fine. So initial random start makes you vulnerable to get stuck in the local optima, as well as the step size also makes you stuck in the local optima. So had the size of the step been very, very large, you are also likely to skip the global optima. I'll show you how it is possible. So if you had started with, let us say this point I'm taking on the left side of the surface, then if your step is very large, even as large as this, it is likely that you have the next step taken as large as this much distance, right? So the distance is traversed in the weight space, and once you have traversed the distance, then only you compute the corresponding error corresponding to the new W1 and new W2. And then in that case, you would have uh, skipped the global minima even. So initially you started with this, you reached here, then from here you reached here, skipping the global minima which is down below this point. So the step size makes it very important to have this gradient descent perform good. Fine. Can you speak out some doubts or some clarity that you have got? Yes. And so considering a step size, the learning rate is selected, and if we still end up in local minima, would we be able to figure that out and continue search for global minima? So there are different techniques like simulated annealing. So this gives you a way to still go for a less greedy approach. It gives you a better, heuristic to get out of the local minima at least for few smaller pits. Okay. Yes, so they could be similar, but yeah, the concept seems to be similar, but then more clarity is needed, and that is why I'm picking up these again for revision. Okay, if you want, I can skip these concepts. So what situation we used gradient descent? So gradient descent is the general optimization algorithm which we can use to find the uh, global optima. The optima could be either a minimum or it could be a maximum. So you can represent your problem as a maximization problem, then you can use gradient descent as an algorithm to find even the highest peak of the surface. You just have to invert the representation of the problem. Okay. So can we make it more flexible so that when the step size is big, we can reverse the traversal when we tend to skip the global minima. So there is nothing like reversal. We have to experiment with the data that we have, and we have to understand that the performance of the classifier is not good. You will have to obtain the best parameter to be used for the learning parameter through experimentation, because there is no written theoretical rule for the learning parameter. It all depends on your underlying data. Yes, you should remember the mathematical computation that has been discussed here right in the slides. Of course, today it is the revision, but in the last class we had discussed, things much at large. Okay. Okay. So then, yeah. So we will not skip. So that is why we are discussing. So we will continue with this. Okay. So equation of line exists, wherein we calculate the value of slope and intercept. So now your perception of the classifier should slightly differ. Here, these W1s, W1, W2, etc. Of course, they are the parameters, but now their role has differed. This is different now, as compared to the one where we were actually using the line and identifying whether a point belongs to one class or another, right? So now we are not viewing W1 and W2 as slope and intercept. Now we view W1 and W2 as synaptic weights, right? So when we see that the error is increasing, then we go a step back in similar steps. So that is the not a correct form of using the gradient descent. We do not have a way to go back. See, these could be the variations in the algorithm. So there could be even tens of different variations of gradient descent existing so far, right? So you can always have your own heuristic to decide what to do, right? So that is what is the work done by the simulated annealing, which has the step size changing based on the search, right? Okay. So we have formula for slope and intercept. So where do we use gradient descent? Um, yes, slope and intercept are there, but you might recall when we were doing those classifiers, we had kept pending a automated procedure for finding those slope and intercept, and in that time we had obtained the slope and intercept based on human intelligence. That means the human sitting in front of that graph decided about the weight and intercept of the line. But now we want our systems to be intelligent enough to decide about slope and intercept. So this is the algorithm which we had kept that time delayed, and this is the time when you can still have weights being treated as slope and intercept for the classifiers that we were doing earlier, where we were actually looking at the decision boundaries. So the same algorithm can also be used to automate the slope and intercept when used in the context of the actual decision boundary. Okay. So equation of line you can know only by optimizing those parameters. The slope and intercept, you can have some range. Suppose you say the slope of the line can vary from 0 degrees to 135 degrees, let us say, and the intercept can vary from 0 to 10. And suppose intercept is W2 and slope is W1, then we can have a kind of grid space with respect to W1 and W2, and then we can apply the same gradient descent algorithm to obtain such weights or such parameters rather there. In two different contexts of the classifiers, we are using the similar algorithm. So suppose you have this line. I am showing you one example. So you will have to see that if I'm having certain points, right? So I'm trying to show you the input space. Input space is this. You must remember that there is a difference between input space and weight space, right? So I'm now drawing on the left hand side of the same slide input space with some red and blue points. And let us say if we have this boundary coming in, which is to be taken as line, okay. So whatever be the slope of this line, let us say the slope of this line was m and the intercept of this line was c. We do not know what value of m and c should there be. In that case, I will take W1 to be representing the slope, right? That is m, and then I will be taking up on the weight space W2 as the intercept. So intercept is taken on W2 um, axis, right? So if you vary your slope from, let us say, range of 0 to 135, right? In the steps of, let us say, in the grid of having a step size of say 5. So if you have 0, 5, 10, 15 kind of different values of W1 being taken and intercept values being taken from 0 to 10, let us say, in that search space. So basically that search space will be identified as this complete search space, right? So on the W1 axis, you can see that I'm typing 135. That shows that the range of slopes is 135, 0 to 135. So the same procedure, W1 will be obtained by finding the initial random weight minus delta W1. This delta W1 will be obtained by using the same expression that we did earlier. So there is not much difference. Only thing is here you are narrowing down your problem only to two parametric space. While in the neural network, we don't just have two parameters, and the similar actually applies even in the other problems where the data is multidimensional data. So in that case, we will have to work with a multidimensional line. And a multidimensional line will not just have one slope and one intercept, it will have multiple slopes and multiple intercepts. So that is the physical, interpretation of classification. From there, we understand the parametric form of the classifier boundary, and then in that context also we can use gradient descent. What we did just recently was about, having the neurons, okay, and having their corresponding weights. So corresponding weights were W1 and W2, and they were taking it as, the weighted sum. So W1 and W2 we took in this context. This is also used as a classifier. A neural network is a classifier. You should understand that the weights basically are representing the classifier boundary. These two have some correlation. Is this okay? We are anyhow classifying the data using the same weights. Only thing is the method of processing the weights and obtaining the output is a little different than the kind of thing that we did earlier using the line as a separator boundary. The purpose remains the same. Okay. Any doubts here? Okay, so see, the thing is, numericals around gradient descent context would not be solvable by hand. You can always write a program to solve it because there could be 100 different iterations through which your you know error is converging to the minimum, right? So from the exam point of view, if you're asking about the numericals, I think understanding this derivation, understanding the concept is very much required. You may be asked to write a program around this. So understanding the weight change, etc., would be very much essential. Fine. Of course, this problem cannot be solved by hand because you need to have multiple iterations to converge to the global optima. Okay, fine. So we move ahead. So here we had actually seen that the direction of the tangent is upwards, but the movement is downwards. Okay. So this expression summation Ti g dash xk, this is the expression that is used for the delta change in the initial weight, initial or the previous weight. And similarly, at every iteration, a new Wj is computed using the old Wj by adding or subtracting this expression of delta Wj. So, uh, learning rate, you have understood the fast or slow learning, right? So there is one alpha as a parameter which is introduced. I think we could touch upon these issues, but very much hurriedly to finish the things in time. So that is why I thought of picking up the similar things to explain more on learning parameters, and then we will move to the feed-forward networks. So alpha is alpha ranges from 0 to 1, right? So if it is 0, there is no learning, right? So if it is 0, that means there is no change in W. The old W remains, the new W remains same as the old W. So that means we need to have at least some learning so that something is added or subtracted from the old W so that we change our position in the weight space. From one W1, W2, we should move to a new position of W1, W2. And then correspondingly the error is computed. And this movement in the two-dimensional, what is shown on the screen is a two-dimensional weight space. So when you move in the two-dimensional space, so let me again remind you that this is a movement in this space, right? While the illusion comes that we are moving in the three-dimensional space. We do not move in the three-dimensional space. The movement is only in the two-dimensional space. But when we move, the corresponding error changes, and then we are visualizing that when the error changes, right, we are coming down to the global minima, right? So this difference is clear. We are actually moving in the W1, W2 space. Now, when you have one point here in W1, W2, you need to move to a new point W1, W2. Okay. And how should this movement be? This should be so optimized that when you move, the corresponding error should have been decreased as compared to the error at the previous point. This is what is the strategy. This is what is the heuristic that we are using, so that the error is every time reducing based on our step taken on this delta W. So when we trapped in the local minima, how do we know whether it is local? So somebody may say that I want the complete classification to be 100% correct. That means I do not want even a single sample to be, classified wrongly. I would say that 0 is my global minima. So suppose you are getting a error of, let us say, 5%, right? Then you would assume that you are trapped in the local minima in this particular case when it is computable and when the global form of the error is known. Okay. So if you have got, so let us say, 87% accuracy, then you would understand that now you do not have a way out and you are trapped in the local minima. Getting trapped in the local minima means that you are not at all having better values as those W1, W2 which are there correspondingly. So with this W1, W2, your neural network is working, or your classifier boundary is working behind, through which you are getting at least some error. Fine. Okay. So yeah. So then we have fast learning like this. So it is still, if it is very fast, you're likely to get trapped in the local minima because of the speed. So speed has to be controlled. It should not be very fast, it should not be very slow, right? So I'm showing you again the animation. If the speed is very fast, that means if alpha is even closer to 1, let us say it is 0.9 or 0.8, then it may go with the full speed and even go and get trapped somewhere in the local optima. Suppose if this is very slow, slow learning, you have very slow and now you are likely to receive a global optimum position. And you were lucky enough to have started with the point on the convex part of it, right? Rather concave part of it. Had you started your initial random start from this point and you had been sufficiently slow in your movements, then you would have got trapped in the local minima. So that's what I told you, that your initial position matters, the initial random start and the value of alpha would matter, right? So this is a function, and so when you have so much effect of this random position, how do we stabilize our algorithm? The stability of the algorithm is obtained by running this algorithm at least 10 times, running the code at least 10 times on the same data. Every time we create the random values of W, um, right, random values of W are created every time, and then we reach either the local optima or the global optima, and then we compute the accuracy of our algorithm for the given data. We take the mean of that accuracy, we obtain the standard deviation. If the standard deviation comes out to be low, that means now you have stabilized with your learning parameter, and irrespective of the global position, if you are getting a very less standard deviation, you can say that this algorithm is very good. But it doesn't happen with the gradient descent. Gradient descent will not be behaving very stably, right? So there are several other algorithms which behave more stable, and when you apply the classification on the validation data, say on the tenfold classification way, then you are likely to get better results in terms of the standard deviation if it is not gradient descent. Gradient descent will give you some average, but then the standard deviation would be very large because gradient descent is sensitive to the random position. Okay. So yes, so how to decide from which side we should have we should start in two-dimensional space to compute to error. So it is just for our visualization that we have a two-dimensional weight space, but in actual you will see the weight space is not this much small because we cannot every time work with one neuron. Most of the problems will require us to have 10 or 20 or 30 or even 1,000 neurons. So if it is a thousand dimensional space or 100-dimensional space, there is no question of the side of the error surface, and there could be multiple such pits or peaks, right? So anything that comes to us is through the accuracy of the recognition using the validation data set. That's why I told you that the alpha parameter is also learned through the experimentation. So most machine learning revolves around experimentations with respect to the data. Of course, your algorithm is good. You have a systematic heuristic to compute your new values of W. That definitely is good. But how it will be reacting to the initial random start, because there is no other way to find the initial weights. You can only start your initial weights randomly, right? So it could start from anywhere. You can have your randomization function available in your software, which you can use to create random value for W1, random value for W2, and so on. So that will form a initial random vector W1, W2, W3, etc., with which you will again start doing the things. You will reach, either you can freeze on the iterations or you can freeze on the threshold of the error. And then you terminate your search, make use of the best W1, W2, etc. obtained so far after a number of iterations, and then obtain the accuracy of classification. So based on that accuracy, you find the mean of those 10-folded experiment, right? The mean is obtained, and similarly now you obtain the standard deviation with respect to the mean. And if your standard deviation is more, then you keep experimenting with new value of alpha. Maybe you initially started with alpha being 0.1, conducted 10 different runs, obtained the standard deviation. So if you increase alpha to 0.2 now and again repeat those 10-folded experiment again, and then now your standard deviation is decreased, then you know that at some point of alpha, I am likely to get the best results. So it is not just the accuracy, it is also the standard deviation, which is the parameter of stability of the algorithm. Okay, so we can say at global minima, the error is minimum. Yes, it may be zero error or may not be a zero error. Yes, it may not be the zero error because your data is so complicated, right? Your data is complicated and it is not yet able to resolve it through any linear boundary. Fine. So then you have to go for non-linearity, introduce more of non-linearity. We will talk about multi-layer perceptron model, which can handle non-linearity by introducing more number of layers of neurons. Okay. So, and then the complexity of the weight space will also increase. Fine. So, I think before we start feed forward and backward propagation, we will just have a 5 minutes break, and then I will come back and start this new topic. Okay.